everyone. Welcome to another episode of the Common Lisp Study Group. I'm your host, Ron Baden with Atlanta Functional Programming. Today, we are going to be continuing our discussion on efficiency issues in Common Lisp. This is covering Chapter 9 of Paradigms of Artificial Intelligence Programming Case Studies in Common Lisp. For those of you who haven't joined us last week, we covered the first part of efficiency issues. We talked about the general history of some of the myths regarding common Lisp and issues with efficiency. And we touched briefly on just how some of those myths are mute nowadays, given the advances in Common Lisp compilers that have been done, well, in the 80s and early 90s since standardization of the Common Lisp language specification and the subsequent hyperspec that was published. The one thing, though, that we covered last week that was in detail, though, was the first part of the efficiency issues, which is the use of memoization or caching of intermediate values during computation. And we kind of dug deep into, different ways of actually handling memoization in Common Lisp then. One thing I wanted to point out is one thing that we didn't cover last week, even though it was implied when we were talking about the fact that with some of the techniques that and optimizations that we made with the memoization approach, you would end up getting um, uh, roughly equivalent code and equivalent speed has the iterative approach. The spatial piece wasn't really discussed. And mainly what I meant is with memoization, there is a um, spatial efficiency cost, and that it is going to be has and grows depending upon the algorithm that you're doing. Usually, you're going to end up having a linear space cost in terms of the actual cache that's going to be held in memory, depending upon how many intermediate values that will end up having requiring. Now, one thing to note is while doing that, you could immediately see the use of iterative approaches in some cases where you could potentially eliminate that cache altogether and just compute this on the fly, and that will give you even more efficient code from a spatial standpoint without actually dealing with some of the runtime efficiency costs that you would normally do with the typical recursive approach. But I didn't cover that last week, mainly because it wasn't part of the chapter. But anybody who's taken a class in algorithms probably are aware that you can actually typically do this. And if folks are interested, I am planning on covering another book after this, which is specifically tailored for dealing with writing algorithms in Common Lisp. It's actually a recent publication from a few years ago, actually. I just acquired the book, so I need to start reading it before we can, do like a little bit of a initial study group on it. Today, we're going to be talking about compilation. Forgive me, I've been dealing with some nasal issues, so periodically it might be clearing my throat just to um, while I'm talking. Um, I wanted to start out with kind of a review of what we covered so far to stage the discussion on the second aspect, mainly because um, while most of you are probably familiar by now with some of the previous approaches that we did with uh, this particular piece of code when we start talking about it, I wanted to at least get other folks who are just joining us at least up to speed. So previously, when we were talking about other systems like Student or Maxima, or in some cases, what's it, uh, ELIZA and GPS, the approach of building each of those programs was fundamentally the same. You have a language of grammar rules, and we designed essentially a search program that interprets, given what inputs was provided to the REPL that we created, um, the commands that it encountered, and we actually searched through the rules for which rule needing to be executed, and we actually then created those rules. Um, One moment. Now, the compiler approach of this would be to take each rule and effectively convert it into a function that can be invoked. So when a particular rule that was created, we could then end up uh, using this rule uh, by invoking the function that actually encounters this rule. And that would be, instead of interpreting it, which would require maybe one or more pieces of code logic to actually go in and do the search, get the rule, do the substitution, and do that, we can actually just invoke the rule, which is just going to be essentially a function call. Okay, and the function call is pretty cheap nowadays. Um, and that function will actually go and execute what's necessary. So we don't actually have to do that search anymore. It actually becomes a constant time operation. Okay, so an example of this is going to be that we're going to be covering actually is part of the grammar that we touch base in chapter 2. So I have to actually pull up the chapter 2 example that we've covered. If you just bear with me for just a moment. Um, this project P Lisp. No, not this one. No, software projects. This projects. PIP is what it is. Okay, chapter 2. Okay. So if you recall in our when we first started with these search programs, and this was before we did the database approach that we saw, the data-driven programming that we saw with GPS and ELIZA and Student. uh, we had this grammar for a basic sentence generation program, right? And this grammar, and we'll even, I'll even go to the simpler version of this, which is essentially this. We have a sentence with a noun phrase and a verb phrase and article or noun, verb phrase is verb or noun phrase, article is the done, and then we ended up, constructing this essentially this set of rules associated with this. Okay. Um, and naturally, a lot of these rules are basically just doing some rewrites for codes before we ended up ultimately creating this generate function that essentially goes through each of the individual rules, the rewrite rules, and we recursively go through and generate the next phrase as part of the sentence that we look up. Okay, so this is what this interpreter looks like. Okay, and if you recall, it was a pretty um, fairly simple operation. If we just simply load this guy up. Um, yeah, okay. And we just generate sentence, for example, we could see that it just generates a simple sentence, right? Now, to make this into a compiler, we have to effectively take these functions that we've created, these rule LHS, rule RHS functions that we created, and effectively um, generate them for a particular rule. Okay, and what I mean by that is right now we're interpreting the rule here. We're getting the first side of the rule in this case here, but what we want is actually um, a what's it a a compiled version of this that effectively does what it would normally do in this case first code to ultimately build us an invocation that would end up being much more efficient than what we currently have here. Okay, that's probably the easiest way of explaining that, right? So there are three cases that we need to really think about for each of these uh, uh, rules that we've encountered here, right? One is we need to think about first off these helper functions that we created. Okay, we have one of verb, okay, and um, noun that we need to essentially think about. Okay, and what we're going to do is we're going to end up calling these different functions, all right, in our actual rule LHS and rule RHS generation. Okay, so let's see how this looks like. So the first thing is I'm going to make a new file so we don't so we can actually have this difference side by side. I'm going to call this ch9 grammar example compiler.lisp just to know what we're looking at. Okay. And the first thing we're going to have to do is we're going to effectively have to rewrite RHS. Okay. Um, there are three cases that we need to deal with if I remember if I remember what the book said. So if every element on the right side of the right hand side is an atom, then we have a lexical rule, which means uh, it's going to be a rule kind of like line 45 in our code. The noun is going to be a lexical rule. Okay, so each one of these is an atom: man, ball, woman, table, cat. Article is also a lexical rule, as well as verb. So we need to handle this first case. All right, the and that's a pretty simple case that we need to deal with. Okay, the second rule that we need to deal with um, is dealing with if there's only one element on the right hand side, then we need to create a helper function that would ultimately build the generated code for it. Okay. Um, and usually this is going to be dealing with, according to the book, the approach they use is using append. So we're going to go ahead and use that case too. And then the final one that was created is if there are several elements in the right hand side, then they ultimately all become um, build a call to build cases. All right, and build cases will end up determining uh, how to handle each of the individual cases by calling them recursively. All right, so let's go ahead and first build this first thing, this compile rule. Okay, um, and I'm gonna try. Actually, you know what? I'm gonna try and see if I could put it in the same file, but we'll see what happens here. Um, you know what? Let's see. Let's see if I could do this. Acquire chapter two. I'm gonna try and see if I can use uh the asdiff generation to actually load my files in order. Um, we'll look into that after I build this into this program. So okay, so let's do this. We do defun compile rule. This will take in a rule, okay, and this rule is going to translate. This function is going to translate the rule into a Lisp function definition, okay, based on what the book was talking about. So, and here's the code from the book, so we can actually go through this. So this is going to take a left hand. Oops, sorry. So we have a do this. Yeah, bring this over here. Okay. So we have a let that will take in the what we already defined. Oh, sorry. And this is going to be our the right hand rule. The right hand side of the rule, and that's just going to use the function call that we just defined earlier. Okay. Right hand side of the rule. Okay. Then what we'll do is given this, we will create a new function using back quote defun. The left hand side of the rule, okay. And what this dot does is the dot operator is going to be a very it is basically a quote operator, so to speak. Um, yeah, we've actually seen this before. Like, I'll show you what this looks like. So if we do rule left hand side, recall what this looks like. If we say sentence, um, this is oops, sorry, my apologies. This is taking the actual rule itself. This is let me go back to this guy. If we take it takes a list of this rule here, right? And yoink, paste, paste this, and what it returns is just sentence. Okay. Um, Now that dot is basically a cons pair that we're creating. So the car is going to be defun, and then the coulter is going to be the rest of this list that we're generating here. Okay. So using this rule that we've defined, we could then do this. We could use cond. Now, by the way, I think that given this definition, we could also write this using def macro. But I will. I didn't try this optimization just yet. When I was looking at this earlier, today I was thinking about that this might be a def macro situation now, but we will see how that works later on. So here is the conditionals. All right. So let's go ahead and actually move this guy down. Okay. If every atom is in the RHS, okay, then naturally what we want is this to be the list one of RHS. Okay. And the reason why I made that a back quote instead of quoting the earlier is because of the fact that that is technically a and we're quoting now the RHS here. So for folks who haven't been following along with our this macroology, the comma separator, remember, is to unquote a particular form. So in this case, our generated code is going to have defun, the left hand, we unquoted the rule, left hand side rule. That's going to take, and that dot operator is needed so that we can evaluate rule left hand side rule instead of actually injecting rule left hand side rule, this code here. Instead of this code here being injected into the final generated function, instead what's happening is this dot operator is saying, okay, take the rule or the next s expression that I've defined after this period and evaluate it and return whatever that value is, has a symbol into this thing. So ultimately, in the case of sentence, we would ultimately get def on sentence here. All right, so that's what that's doing. And then the comma operator is just, like I said, it's unquoting the expression. So comma RHS is just effectively allowing us to um, inject whatever the value is there instead of treating it as an S expression. So that's the first case. We've already uh, talked about um, uh, if everything is an atom, it becomes a lexical rule. The next thing is length equals. Do I have? So I think this is a utility that um, Norvig defined in his code. Um, length equals. Yeah. So we need to first define this function here in our file. Um, right. Let's just grab this guy. Oh, sorry. Grab this guy. Copy. Okay. And we need to define this guy above this here. Let's paste this. And there we go. Give length equals 1. And all this is checking if the if it's a cons value and the critter is null. Okay. And so if we know that it's a single rule, then we need to essentially call build code for this guy. So this ends up being build code, which we'll define in a second here. RHS. Okay. Okay. And oh yeah, because this is a list, we need to actually go and create something else. first. Okay, I heard a question pop up. Give me just a second. Oh, here's a comment. Okay. Okay, so the question about length equals one. Length equals one, as you just is a function. Um, yeah, that's right. Okay, so someone asked about length equals one, and just misread it in the video. Okay, so let's go ahead and build code. Eventually is going to be something that we're going to define. Um, I just haven't defined it yet. One of the nice things about Common Lisp is you can define as you go along. Um, so we'll hopefully get it defined once it's available. Okay, and then the last thing that we need to define is the true case. Okay, now here is going to be a little different. Okay, let's see. So we do true. Actually, it's true. No, it's no, I had it right. True, and then we do cases. Okay, and this is going to basically um, do a random on the length of A to build the actual cases. And the reason for that is how if you recall what the if it's an unknown rule, it's picking, um, or if it's a rule that if the left hand side of the rule, sorry, if the right hand side of the rule has an unknown number of cases, we need to actually go and build up each of those rules itself. So what we need to do is just first get the length of the right hand side of the rule, and then we need to use that to actually go and loop through each of those individual cases. Okay. And the reason for and this is mainly because we're using this to well, you'll see what happens when we use when we define build cases, how this is actually going to be leveraged. Um, and then finally we have this, which is um, at comma at actually the book uses an old notation that I don't recall seeing, but we will see what this is. It uses a dot at, and I don't know what that exactly does, but we will try it anyway. Build cases with 0 and RHS. Okay, so we compile this rule. Error saying, what's the error? Let's see. More than one object follows dot in list, line 4, column 30, position 139. This is here. This is 29. Hold on. Let me see this again. Clear REPL so I can actually look at what it's complaining about. Okay. Line 4, column 30. Line 4, column 30. So maybe I don't, oh, you know what? Maybe I don't need to do this. And I could just do the evaluate step. See what happens if I do this. Okay, so this has to be a back quote. Okay, so that's fine. So now we fixed one issue, but we got back the other issue about the dot being. Okay, let's see if this actually fixes this issue. Um, okay, compilation successful. Um, so I want to try just a simple example, and that is going to be with article and see what it does, right? So let's see here, compile rule, because this is going to be a valid rule. The other two, we need to actually build the other two functions, but we can actually execute this code, at least for the first case, by just making sure that we write the A. And what happens is yeah, okay. So the dot cannot be used in that case. Okay, so this is fine. And you can see the generated code has it expected for um, article for the at least the function call being just a simple you know delegation to the one of helper function that we defined in the previous chapter. I mean, sorry, in chapter 2. Uh, so let's get build case going. So what does this look like? So this is pretty simple. What this is going to be also dealing with um, appending together the multiple constituents in a recursive manner. So if you have build code, okay, and this is some code, okay. Let's actually let's call it a choice here. Choice to match what the book has. Um, and what this does is it's going to just I'm going to write the code and then we can write the comment on this. This is just going to um, create a list of all the constituents that we've constructed. All right, and build each of one of them individually. All right, so um, here we have also three cases that we need to deal with, okay? First is the natural base case. If it's null, okay, what do we do? Well, we just return nil, okay? If it's null, we just return nil, okay? Next, if we have if we have an atom, all right? If this is just a simple choice, okay? A symbol ultimately. Well, we need to create a list of this and return it back because ultimately in our construction we're going to append everything together, and you'll see that in the final construction of this. Okay. Next, if we get exactly only a list of length 1, all right, then we're just going to return that because that's what we want. We actually want that. And then the default case is we're going to go through each one of these, all right, and we're going to append them together, okay? And what we want is we want a generated code that would ultimately take each of these choices and then um, execute them, right? So this is going to be a map car, all right, that will transform this list of choices that we have by calling build code on each of them. Okay, build build code on each of the choices. Okay, and what that will do is construct this the situation where each of those build codes are individually built. Okay, so now what we will do is we're going to have to create a list of case clauses ultimately that would be used by this case compiler that we're creating here. Now, this case compiler is taking one of the rules here, this random rule that we're getting. So if this length is 5, we're going to pick a random element from 0 to 5 to actually figure out which part of the case statement we're actually going to trigger. All right, and that case statement will need a number and the rule that we're going to actually invoke. So what this is creating, it's generating from the rule a table, okay, so to speak, of jump points to actually go and invoke the particular um, function call or particular set of code that will ultimately call to actually generate the sentence that we were seeing earlier. So let's see how this is going to look like. So we're going to do defun build cases, okay? And build cases is going to take a number and a set of choices. And what it does is that when we have a non-empty list of choices, okay, we're going to essentially do a cons, okay, with the first list being the number, okay, and we call build choice on first choices, the choices, with build cases on the rest of the choices. So this is our recursive call. Okay, and now naturally we'll say number plus 1, or I'm going to use just 1 plus here instead of say 1 plus. Okay, and um, our rest of the choices. Okay, so let's build this guy. There is style warning. Let's build this. Build that again. What? Hold on one second. Build. Oh, sorry, not build choice. I meant build code. There we go. Build code, and we're now good. So let's see how this looks when we actually call compile on individual rules. All right. Um, so let's try sentence. Okay, sentence. We have um, noun verb pair here. Okay, let's go and grab that here, and let's call each of compile rule on each of these individual ones, right? So compile rule on that, and we'll see that it builds this function that calls build code first RHS. All right. Actually, that doesn't look right. Second. Oh, dummy. I should have done this to be a back quote. My apologies. I think this was a back quote. Um, oh, yeah, my apologies. This did not need that. Done. So let's do that again here. Shift code. Okay. So this actually creates what we expect. When you compile the rule with the sentences, you will see that the left-hand side, the LHS took the left-hand side of the rule that we constructed with the for the arrow, and the right-hand side transformed it into append to noun phrase and verb phrase. Okay, which is kind of nice, right? But we're not done just yet. Okay, we can actually write these rules themselves no longer with uh, uh, well, let's use this approach. Once you have compile rule this way, you can actually do an eval. We could write a simple function here. Okay, here like do list. Okay, on rule in our grammar. Okay, and um, uh, we could actually go and build each of our rules once this is done. Um, so that's pretty simple. We could just do an a simple approach is just to do an eval on compile rule, rule, right? And what we've done effectively is we redefined all the stuff that we've done earlier here with our compiler. Okay, so to really, take this home, we could just, redefine this here and restart our common Lisp so we can load up our compiler only in this file, and we could actually go ahead and see this regenerated, no problem. Okay, so let's do that now because I think this would be a good time to actually show that off. We need obviously our one of in our random element because this is going to ultimately be used when we build that. And also we need generate because when we call a specific function, ultimately this is going to be used at some point as well to actually generate our code. Okay, so I'll do that. Actually, let's do this here. Okay, and let's restart our Lisp to check this out. Okay, let's go ahead and reload this file. And hold on, there's something I'm missing in here. Rule R. Oh, I forgot to grab the RHS and LHS stuff from that file. Okay, give me a second. Um, okay, so now let's go and load this guy. undefined function rewrites. My apologies. Let me go here and put that in there. Up. Okay. Okay. So let me just do one more test here. Okay. So now everything's properly loaded. I mean, you didn't have to do that secondary restart, but I just do it just in case some symbol might be, defined. It's always good to deal with it with a clean image. Um, so let's see what happens when I call generate sentence here. So you see, we didn't actually break anything. Okay, generate noun phrase, because it's literally just calling our code. Okay, but it's no longer using this grammar functions anymore. We've generated the grammar itself. Okay, so we generated each of the individual. What I mean is we generated each of the individual rules. Okay. Um, One thing that's particularly interesting is if we uh, look at um, noun. I'm actually particularly interested in um, the rule case that was provided with let's see here. Let's try here the case to generate the final case here. We would have to make a small change. Let's see. Uh, yeah. So noun arrow man ball woman table cat chow chow. Let's see if I've actually handled this case here. Ah, it did not do what I expected it to. We've actually saw this case here. Let's go ahead and fix that, because this is the default case that we were talking about earlier about the cases of building the cases for each of the individual choices. Um, go. This needs to be that. Okay. Let's try running that again. Okay. So in the default case here, we could see that we can actually generate each of the individual cases here, and we're getting a random number between 0 and 6. And depending upon what number we get, that's what the choice we end up generating for the sentence generator. All right. So that's pretty cool. Um, this can also be used for generating rules, but before we do that, there is one thing that the book also defines that I thought I would just quickly cover. You see how we are doing this do list here? Normally, a couple things. One, we do eval here, and we're actually loading the image and we're interpreting the function definition into the code. Now, most of the time, most common Lisp compilers, I'm almost certain that they don't. In this case, like in SBCL's case, eval also would and I don't know, I may be speaking out of turn here, but there is eval, which is normally associated with interpretation, and then there's compile, which is normally associated with actually compilation. And usually, if you want to generate this compile rule will generate the actual function definition. Eval will evaluate it, but after this, you would also want to actually add compile to actually go in and compile the damn thing and optimize it. Okay. Um, I don't know if eval is pure eval in SBCL. Folks who may know, please go ahead and let me know. Um, just mainly because when I look at Sylvester, it looks like it compiled them. All right, so it recompiled and redefined the sentence. But did it compile it in terms of interpretation, or did it compile it into machine code? I don't know. I'm just using what the thing is there. Okay. Um, so there was a question about the dot at. There was places where in the book, if you actually look at the book, where the publisher I think made some mistakes on generating a comma where it should have been, and instead using a period instead of a comma for the comma operator, which is the unquote operator when you're dealing with macros. Um, and so there were some mistakes that were made when we converted them into dealing with the when I was converting it into the code that I was putting on display. Um, so there's this approach that we've actually go and defined. We can actually do the star grammar. We could create the database of grammar and then compile each of them individually. But you could also just simply create a macro that will compile this in real time, right? Um, and effectively, uh, what is this grammar rule if not just simply a macro that we could define called um, def rule, okay? And here you can use rest or body. Body doesn't really matter. Body is basically the list of forms, okay? And this basically can just be called to compile rule, all right? And this will ultimately do essentially the same thing that we were talking about. Um, and what this does is we can actually now write, instead of this code here with this macro, we can actually just say, and I'm going to show this by doing this a little bit differently. I'm going to comment this guy out here for now. Oh shoot. My apologies. Okay. Okay. And I'm gonna go ahead and where is this guy here? Also comment this guy. Oops, sorry. Oops, I have to do this. There we go. And I need to unintern the grammar. The only problem is this is going to have everything already defined. So let me restart my Lisp one more time to show this piece. Okay, so we now define that. We have our def rule. And now instead of our grammar being ruled written that way, we could also write it this way now, like functions, essentially. So sentence, arrow, oh, not space arrow, noun, phrase, verb, phrase, and oops, this should be actually a list here. And if we actually do a macro expand of this guy, you can see that this just generates our function the same. Okay. So this is another approach to actually go and building um, this case here, and you can try out all the different other approaches on that. But the goal of this is fundamentally the same. You'll actually take the rule and compile it to a more efficient execution set of code that can then be further optimized by the Common Lisp compiler and then the Common Lisp and you can add error handling too at that point too as well. So it makes things a little bit easier for you to, more or less be able to debug and even add some more features for people to use your DSL. This is actually a very common approach, folks, in Common Lisp. You define kind of a set of macros that create this kind of problem-specific language for the particular domain that you're trying to deal with. And the advantages of creating this kind of compiler is the lower forms that most people don't need to be aware of can be leveraged at the compilation level, and you end up getting speed of execution. All right. In this particular case, according to the book, the compiler that we've just written for generating sentences is actually uh, can generate close to 200 sentences um, uh, pretty quickly, which is pretty interesting. And we'll deal with another compiler later on in this chapter when we are dealing with stuff. But I would say that with with that we are kind of at the end of today's discussion. Um, I wanted to talk about um, delaying computation here and lazy evaluation effectively, but that section is a little bit more involved, and I didn't get a chance to really understand some of the approaches there. So I want to take some time to actually read through it again, just to see what is there. So we're going to end a little early, but I'm going to open the floor to questions and comments.
I have a question that is about Emacs tooling. So it's not specifically about Common Lisp. So I don't know. I
No,
could
no,
have
go ahead. I mean,
an idea.
if it's a Lisp related question, if it's Emacs tooling for like is it for general Emacs tooling or Common Lisp
Yeah, it's
specific?
pretty generic. So
Okay.
the question is, I let me share my screen and then I can demonstrate what the question is about. Allow entire screen? No, just Emacs. Share. Okay. So I just got done. Uh, I
Hold on one
was
second. So
okay.
our audience can actually see this. Let me share um the
Share what I'm sharing.
yes, share what you're sharing because we're now because unfortunately folks who are with us, we're using Jitsi but unfortunately Jitsi was giving me some trouble, so I switched to OBS, so I have to actually hook OBS to our Jitsi tab.
Oh, okay.
So just give me just
Um,
one, bear with me just one
while
second.
while you are doing that, I'll describe the issue. So what I'm doing is I have some code that works, and I'm like doing practice runs, going through the code, deleting bits, rewriting them from memory. And what I would like is while I'm doing that, for I have a test that I can run, and I can describe like when the test is successful, it should have no standard out, and when it has standard out, then there's an error.
Could you
So what
show
I
that code again and repeat what you just said, just so that folks can
so
understand what you were saying earlier?
So what I'm doing is going through, I'm like practicing code. So here is code for finding the shortest path between node A and node B.
You're right.
And I'm going through and deleting some code and then seeing if I can recreate it from memory. And let's see, I want to re-add the neighbor, and then so I would do that. So I would like delete this line of code, then switch to this and run this. So I'm running this script, which if the output is empty, that means the test succeeded. Then I can switch back to the code and then do it again for a different line of code. Like I could delete that line and then rewrite it and then switch back and rerun it. It would be really convenient. Like I'm pretty sure something exists like this somewhere. I just don't know how to find it. So I was thinking like maybe um, rather than switching over here, it, see what the result is, then switching back. It would be cool if the running could happen like Emacs could just run it every time I hit save, and then maybe there's an icon in the lower right or something, or somewhere up in the side that like has a red X or a green check mark,
So
depending on
I
whether the
am
test
almost
was
certain
successful.
that I understand the question now. So I
Cool.
almost am certain that there is a way to essentially create a watch,
Yeah, I'm
a
pretty sure I
file
could write
watch.
the code to do it, and
But
I
no, no,
think I will
I
if I don't.
understand that,
Oh,
but
okay.
I'm just saying that I'm almost certain that outside of
That's
you
such a
writing the
thing.
watch, that somebody has probably already written a plugin that has a
Cool.
watch on a file. I just don't know one off the top of my head. That's a
Yeah, I'm in a
that
similar situation. Okay.
that's a.
I
But I know
will
FS
ask.
Watch exists. You can easily do that with the essentially polling on the file, and every time the file changes and looking at the
Oh
stat,
yeah,
um, you
yeah.
can actually, yeah,
I've written a tool like that that will commit and push every time I do file save, and it uses on Linux. It uses iNotify,
right.
um, and it doesn't do polling. It's a I don't know
Well,
whatever iNotify. It's not really
I
push
notify I think
exactly.
uses like K-poll or something like that. I thought like it's something
Uh, it falls back to that anyway. Um,
or lib
yeah. So
event
like
or
I'm
lib
pretty sure
event.
I can write I'm pretty sure I can write such a tool.
Yeah.
I was just thinking probably someone has done that already and hooked it into Emacs and like made a little icon thing. Um, right after this, in 24 minutes, there's another meetup, functional programming, and a lot of people in that meetup use Emacs as well. I'll ask there.
Okay.
Uh, yeah. All right. Cool. Thanks. That was what my question was.
All right. Great. Um, and let
Yep.
me see if there's any other questions on the. No, it looks like we
Uh,
have no
on the
questions
YouTubes.
on YouTube's. So with that, I hope all of you enjoy your Monday evening. Thank you for joining us. Next week, we're going to be talking about essentially delaying computation. Hopefully, probably go into a little bit. I
Cool.
hope we don't go into a discussion on Haskell versus Common Lisp, but I probably will bring in Haskell just to talk about some of the differences. Just
Yeah.
because since we are talking about delaying computation and that's basically Haskell's bread and butter, it's probably
Yeah.
a good idea to effectively
At
talk
least
about
compare and
yes, at least compare
contrast.
and contrast. So with that, have a good evening, everybody, and see you next week. Peace.